project for Civil Engineering 4210 at Ohio State, or Physics of Sustainable Buildings. So the main issue that initially led people to designing passive homes is the same as what we've talked about in class throughout the entire year, which is building tight and ventilating right. Um, so essentially, that main idea, they took it and pushed it to an extreme, including as much insulation as possible and as few air changes per hour as possible, basically, in order to reduce as much energy cost as possible, due to an energy crisis that happened in the 70s that we'll talk about a little bit later. Um, so, like we talked about in class, 40% of energy consumption in the US goes to buildings, and um, so passive homes basically are attempting to lower that percentage, on the residential front, and then eventually, hopefully, into the commercial front as well. So, residentially speaking, they're also trying to combine the idea of passive homes with multifamily homes, which will allow for an even greater reduction in residential energy consumption. So, as previously stated on the slide before, the general concept is basically to push insulation to a maximum and then also capture energy in ways that you wouldn't typically think of in construction for a house. Um, so these are two main figureheads for passive homes and their introduction to the world. This is Dr. Wolfgang Feist from Germany and Dr. Bo Adamson from Sweden. So the concept started in the US initially with an energy crisis, and then Europe ended up taking the reins and pushing it one step further. So these guys, created the first standards on passive homes, and they basically wrote the book. So um, they decided that the homes must meet an annual load of 4,750 BTU per square foot per year, and also zero point 0.6 ACH 50 air changes or lower as well. So with these strict standards come a list of concerns regarding passive homes and their implementation. Here we have a picture of a passive home in the United States, which utilizes typical features such as heavy insulation, smaller windows, and solar facing windows. But the concerns of passive homes include the curb appeal of the house, essentially, is greatly diminished. Um, they're going to be a higher upfront cost, which is an issue for some buyers, meaning that the payback period over the course of the house is going to end up being longer, but there will be more savings in total depending on how long they own the home. Um, so the ideas behind passive homes aren't transferable to commercial buildings due to the fact that there are other factors, with commercial buildings, such as employee morale, um, just general appeal of the building being more important, and size of the building that make passive cooling and heating more difficult, and also the airtightness requirements are definitely helpful for temperature control. However, as discussed in class, um, there are other comfort requirements such as CO2, um, part- particles in the air, and more, that could be hindered by lower air changes. So typical technologies in passive homes include very heavy insulation. So these are almost always going to be R50 or above for walls and even higher for roofs in order to combat that thermal component from the sun. They're going to have triple pane windows for the most part, at least double pane, in order to lower the high loss through windows. They're typically going to have smaller windows and also coatings to prevent radiation from escaping the house. Um, so, as seen at the 4-H building at Ohio State, there are the option for below ground heat wells, which capture the very stable below ground temperature of about 50 degrees Fahrenheit, um, and capture that and bring it back into the house. They have more optimized heat exchangers than other buildings. They have a very airtight construction, as mentioned, and then at joints in the house, there's reduced thermal bridging. So as we talked about, the studs typically have some thermal bridging that happens, and then anywhere where there are more conductive elements, there's going to be thermal bridging that happens as well. So um, they do as much as possible to limit that. Also, there are typical sustainable practices, such as in the last picture, there were solar panels and more in order to reduce energy costs, um, paying for fossil fuels. So here's a little history behind passive homes, basically the most important key moments in its history. Um, so starting in 1973, the oil embargo of 1973 basically led to an energy crisis in North America, meaning that North America, specifically Canada and the United States, wanted to rethink homes in order to reduce the cost at the consumer level and also reduce the usage um, of fossil fuels and creating overall better energy efficiency in residential areas. So in 1974, the Locale House is designed by the University of Illinois, and that was basically a proof of concept for passive homes as a theory. Um, they kind of went out and actually did the work. They made it feasible um, with limited technology compared to what we have now. So then in 1979, William Sherliff, who is a Harvard physicist, put out a press release talking about super insulated homes. While they still didn't have the passive home name, he popularized them in a big way and opened the public's eye to alternatives for home design. And then in 2007, the Passive House Institute United States, or PHI-US, was founded, basically jumping off the back of the Passive House Institute by those two doctors in Europe, um, and they basically just became a leading organization for all things passive house related in the United States and brought over the knowledge from Europe into the United States. So continuing with PHI-US, they created a certification process using the Department of Energy grant, and here we have a map of all of those certified homes um, and other projects in the United States. As you can see, they're clustered generally um, in the Midwest, up and then around the East Coast and West Coast. Um, Not too much in the plains areas. Um, so those are totaling 4.2 million square feet of certified or pre-certified FI-US passive projects. Um, and those are in 37 states and provinces. So that is including Canada. Um, and basically, they're favored in states with more temperate climates, as well as some up in the northeastern United States, which have a little bit harsher of climates, and northwestern as well, which have more harsh climates. All right, so moving back a little bit, this is the locale house designed by University of Illinois small home council. So they were basically the first to test the concept of passive homes in the United States, and their overall goal was to build a house with one third of the energy consumption required by the 1974 insulation standards. Um, so they basically just wanted to prove that houses in the United States could actually um, legitimately reduce the amount of energy consumed by buildings and try to put an end to the energy crisis, or at least slow it down to some degree. Um, so this home was relatively primitive compared to what passive homes can do now. They have, um, they just have insulation at a maximum, and then through orientation of the house, they wanted to get as much heat through uh, through the solar radiation as possible through the windows. Um, and that's basically all for the house. But as we can see moving forward, the the technology's increased greatly as mentioned on the technology slide. So speaking of improved technologies, this is a Yellow Springs passive home in Ohio, in Yellow Springs, which is the first FI-US certified passive home in Ohio. I, be- I believe up until this point, there's been at least one other in Ohio. So some of the key insulation that this uses is 20 and a half inches of fiberglass, zero point 0.4 inches of OSB, and 3.5 inches of foam on the roof. So as we've seen in class, the roof is the most important part for insulation against hot temperatures due to the fact that it's grabbing so much of that sunlight throughout the day. Um, and then on exterior walls, there's going to be 13.5 inches of fiberglass, which is an insane amount compared to um, the houses that we were looking at typically in class at around 6 inches of fiberglass insulation. Um, and then also the air tightness of this house was 0.32 air changes per hour in ACH 50. So once again, as discussed, this can be a good and a bad thing. The temperature um, is definitely going to be easier to control with low ACH, but you're going to see that other types of filtration might be needed, and um, it might be necessary to flow air through the house or flow air around the house as opposed to through the house in order to fully clean the air and make it comfortable for the residents. So as discussed on the slide with the map of the 5 US certified projects, there's a large difference in what is viable as a standard for a passive house in different climates. So here's a little bit of math in order to show just exactly how different it can be state to state. Um, so I used a very temperate climate in San Francisco, California, and a little bit harsher of a climate that might be familiar to some of you in Cleveland, Ohio. So basically, I wanted to choose the cold days out of the year since I knew that that was going to be the largest difference between San Francisco and Cleveland. Um, so I assumed that the inside temperature was 20 degrees Celsius for both cases because the um, we want the inside temperature to remain constant, whereas the outside temperature on the coldest day of the year in San Francisco was 6 degrees Celsius, and the outside temperature in Cleveland on the coldest day of the year was actually negative 14 Celsius. A little bit of a typo there. So here we can see a calculation we've seen many times, the flow per unit area, or um, temperature driving force over the R value. So we have the delta T's for each area, and then below we have the total R value for the wall, the roof, and the windows combined, um, which we want to remain constant between the two areas, just in order to show how big of a difference the temperature driving force has. So here we have the final equations for flow per unit area in both San Francisco and Cleveland. Basically, you can see Cleveland has about 3 times higher, approximately, of a flow per unit area in terms of heat getting out of the house, and that shows that there's a quite a large difference between those temperate climates that are more likely to be able to have passive homes and that of something like Cleveland, or even colder areas which are less likely to be able to house those passive homes. Um, but this has to be taken into account with other factors such as interest in passive homes um, and also money willing to be spent on environmentally sustainable practices. As we saw in the map from PhiUS, there was a lot of flyover state, for lack of a better word, in the middle of the country that had no passive homes, and that was likely more due to a lack of interest than a lack of viability for passive homes. And then here is the works cited, and that concludes my presentation. Thank you very much for watching.